Welcome to EDU World Space.
This is chapter 21, problem number 64. We're asked what would change electric field wise if instead of having a dipole of one positive, one negative charge, if both charges were positive. So in part A, we're asked to show that at any arbitrary point along y direction, the electric field would be equal to 2q over 4 pi epsilon naught r squared. We're asked to prove this. So the way to prove this is very easy, right? We have 2-point charges. They're going to generate, each one of them are going to generate an electric field at the point r away from the center, right? This distance is given to us as r, and this is L. So when we look at the fields, obviously the magnitudes of these fields are equal to each other, right? Because the distances from the charges to the point are equal to each other, and the magnitude of charges are. We notice one thing, that the horizontal components of these electric fields are going to actually cancel each other out. So as far as the total electric field is concerned, at this point that we're interested in, we have twice the y component of this electric field. What this means is, well, the y component of electric field is the magnitude of the electric field coming from a single one, right? Because we're multiplying it by 2 times the, so if this angle is theta, then this, phi, then this angle is also phi, then we're going to take the sine of phi, right, in order to calculate the total and multiply it by 2 because we have 2 electric fields. Now, what is the electric field? The magnitude of the electric field coming from a single charge is kq over, let's call this distance d. As you can see, this d is the hypotenuse of this right triangle. Let's call it d squared, where d is actually l squared plus r squared, square root of this, correct? So sine phi then would be equal to, let's look at this triangle again. Sine is across, which is r, over hypotenuse, which is d. We also said that d equals square root of l squared plus r squared. All right. Now let's write the electric field in terms of L and R. K, Q, D squared will be L squared plus R squared, right? So let's combine this and the sine phi and put it in the total electric field equation on the next page. E total would be twice the electric field, which is KQ over R squared plus L squared, and sine phi was R over R squared plus L squared 1/2, right? The square root of that. Then if we arrange this, we have 2kqr in denominator of r squared plus L squared 3/2. Now we're going to make an assumption. It's also something given in the question to us. R is bigger than L. So we can approximate the solution in denominator to be r squared 3/2. All right, assuming that L is really small. Then these are going to cancel out. The E total is going to be equal to 2kqr over r cubed. Now, you see these r's are going to cancel out. Then we have 2kq over r squared. As you know, k is representing 1/4 pi epsilon naught. We have 2q over r squared. This is exactly what we were asked to prove, right? So we've done it. In part B, we're asked why this electric field is depending on 1 over r squared and not 1 over r cubed like a dipole? Well, the answer is easy, right? Because this arrangement is not a dipole arrangement. This is simply 2-point charges having the same sign and generating an electric field. So if we go far away, far enough, that these two individual charges are going to appear to be a single charge of magnitude of q plus q. So let's say a long distance away, they appear to be a single charge of magnitude q plus q equals 2q. So then this explains why the electric field is proportional to 1 over r squared there and not 1 over r cubed like a dipole. When you look at this electric field, this exactly tells you that, right? That as if you have a single charge that has the magnitude of 2q, and we're looking at the electric field generated by that.